Everyone. Now, as a complement to the numerical method course that I just started with it, every week I will have a set of practice problems that I will try also to solve them to enhance the information I have in the lecture as well. So this is the first set of problem solving, and this will be about the errors, number systems, and error propagation. So let's start with the first question here. We have the x true. The true number is 2.0000. We have to approximate. The first one is 1.9999 and the other one is 2.9999. We want to find the true error, the rate of error, and the number of significant digits in the approximation. So we'll start with the 1.99. So to find the true error is very straightforward. You subtract the true number, which is 2.0000, minus the approximate, which is 1.9999, and this will give me 0.0001. So that is how you find the true error. To find the relative true error, you subtract the true error, the 0.0001, divided by the true number, which is the 2.000, and you will get 0.00005 or 0.005%. Finally, we want to find the significant digits, okay? So we take the absolute value of the percentage relative error, which is this one, the 0.005, and this will be less than or equal to 0.5 times 10 to the power of 2 minus m, and m is the least, at least this is the, we have this number of significant digits in the true answer, okay? So we want to find m. When we solve for this, clearly your m will equal to 4, because when m is 4, this is equal to 10 to minus 2, this becomes 0.005, the same as this, and this is equal or less. So m here, so we have at least 4 significant digits. Now, when you go to the other number, 2.9999, we do exactly the same thing. So we will basically subtract 2.0000 minus 2.9999, and this will give us minus 0.9999. The relative error, which is minus 0.9999 divided by 2.0000, and this will give us minus 0.4995, which is equal to minus 49.995%. Finally, we take the percentage relative error, the absolute value of it, which is the 49.995, and this is less than or equal to 0.5 times 10 to the power of 2 minus m, and obviously from this m is equal to basically 0, because when m is 0, this will be less than or equal to 15, which would make it this, which is true. Okay, so that is the first question: how to deal with the true and the relative error. Now, the second question says convert 0.8, which is in decimal system, to the binary representation using 8-bit approximation. So basically what you do, you take the number here, you multiply 2 times 0.8. The number here is 1.6. So the number after the decimal is basically the 0.6, and before the decimal is 1. Now you take the 0.6 here and you multiply it by 2. So 2 times 0.6, which is equal to 1.2. The number after the decimal is 0.2. The number before the decimal is basically 1. We take the 0.2 and multiply it by 2. So this becomes 0.4. The number before the decimal is 0.4. The number before the decimal is 0. Take the 0.4 2 times 0.4, it is 0.8. The number after the decimal is 0.8, before the decimal is basically 0. Now take the 0.8, so 2 times 0.8, this is 1.6, here is 0.6, and here is 1. And you see now, we start to have a repetition. 1, 1, 0, 0, then we'll start to have a repetition after that. So when you have the 0.6, 2 times 0.6, this is 1.2, which is exactly like this. Before, after decimal is 0.2, before the decimal is 1, and if you repeat, you will find this is 0 and 0. So your number, the number will be the radix, and you will have here 1, 1, 0, 0, 1, 1, 0, 0, and this will be repeated. You can write it as 0.1, 1, 0, 0, and you put this so to show that this will be repeated down the road. The third question, now we do the opposite. We want to convert this number into the decimal representation using 8 significant digits, okay? So start from here. So we will have 0 times 2 to the negative 1 plus 0 times 2 to the negative 2 plus 1 times 2 to the negative 3, and so on and so forth. 1 times 2 to the minus 4, plus 0 times 2 to the minus 5, plus 0 to the minus 6, plus 1 times 2 to the minus 7, plus 1, 2 to the minus 8. Then, of course, these are all zeros. So you add the rest. So we'll have 0.125 plus 0.0625 plus 0.0078125 plus 0.00390625, and the total will be 0.199218751234567 significant digits. Now, the third question, or the fourth question here, we want to convert 12.6 into binary floating representation. Not just a binary number, but the binary floating representation using an 8-bit system. We will come to this. So first, we need to convert the 12 into a decimal system. So we have here the number 12. You divide by 2. Now, for the whole number, you divide by 2. For the decimal, you multiply by 2. So here we have 6 remaining 0. Take the 6 divide by 2, it is 3 and remaining 0. Take the 3 divide by 2, it is 1 and remaining 1. Take the 1 divide by 2, so this is 0 and remaining is basically 1. Now once you reach the 0, you reach the final number. So the 12 in the decimal 10 system is equal to 1100 in the binary system. Then we need to find the, or calculate the point 6. Now here we will have the point 6. Again, the same thing as we did in the previous example. 0.6 times 2. You will have here 1.2. The number after the decimal is 0.2. Before is 1. Then here, take the number 0.2 times 2, which is basically 0.4, 0.40. Then 0.4 times 2, 0.8, 0.8, and 0. Take the 0.8 times 2, it is 1.6. So here it's 0.6 and 1. And then take the 0.6 times 2, which is 1.2. Here it is 0.2 and 1. And you see now here start to repeat itself. Same the previous question. So we'll have this is 0, 0, 1. So basically your 0.6 will be equal to 1. point radix, and then 1, 1, 1, sorry, 1, 0, 0, 1, 1, 0, 0, 1. Okay, so your 12.6 would equal to 1100 point. So this is the whole number, and then we will have 100110001. Okay, now we need to put this as a floating point, so we move the radix 1, 2, 3 positions here. This becomes 1.1 0, 0, 1 0, 0, 1, 1, 0, 0, 1, and this is times 2 to the power of 3. Okay, now I want to put it as an 8-bit floating representation. Okay, so the first one is the sign of the number. The sign is positive, so this is 0. The second one is the sign of the exponent, which is also positive, so this is 0. Then the exponent is 3, so these 3 places is for that, so it becomes 0, 1, 1. So that is for the exponent. So here is your exponent. And then finally, the last 3 digits will be for the mantissa. So you basically, you ignore the 1 because it's always there is a 1 here, and you count 3 numbers, 1, 2, 3. So you will take these 3 numbers, 1, 0, 0. So that is the binary floating representation using an 8-bit representation. Finally, the last example is basically about the error propagation. Okay, using a mathematical operation like here. So here have multiplications, you have division, okay, and you know the error percentage in each one. So in A is 1%, B 3%, and so on and so forth. Now, so the percentage of delta B would equal to, start with the first number. Now take the exponent here, becomes equal to 3 times the percentage error of A, and then you add to it B squared, so it becomes equal to 2 times the percentage error of B. Now for the item that is divided, you also add the error, but this is root of half, so this, or minus half, so this is 1/2 basically, times delta percentage of the error C. Finally, D is by itself, so it is percentage error of D. So now here you start to add the errors. So this is 3 times percentage of A is 1 times 1 plus 2 percentage of B is basically 3 plus 1/2 percentage of C is basically 4 plus the percentage of D, which is 2. Now when you add all of this, so this is 3 plus 2. Okay, so this, sorry, this is you multiply, this is not, so this is 6, 3 plus 6 plus 2 plus 2, which is equal to 13. So this is the 4 errors you have for each mathematical manipulation. So that is basically some examples about the error and error propagation and number representations. And as we move in the course, we will have the lectures in one playlist, and then you will have the practice problems in another playlist to enhance the knowledge about the topic.